the x component of the vector curve derivative. So negative 3 sine t. And then I could say dt, right? But I'm going to do this all in one integral. So I have plus now, I'm running out of room, plus 7 times x, but x is 3 cosine t. That ain't so bad. Plus, square root of y to the fourth plus 1. Y to the fourth? So 3 sine t to the fourth. What's 3 to the fourth? 81 sine to the fourth t plus 1. And then at the very end of that, the derivative of y, which is this one, 3 cosine t. All of that, right? dt. Anybody feel like integrating this? That one's not so bad, right? Antiderivative of 9 sine t. Thumbs up. This one? No. Nobody? I don't think anyone in this class is doing that one right there. That's a tough antiderivative right there. Oh, shit. No, I forgot. This has to distribute through. So maybe you might be able to get. But still, it's not fun. And this, I don't feel like messing with that either. This looks like it could be kind of tough, huh? So this is where we go, maybe not. Because this is a nice closed curve. It encloses a nice region D. And maybe it'd be easier if we actually use Green's theorem. So we're just going to go like no way here, right? No way. I'm not trying. So using Green's theorem, all I need to be able to do is convert this to the double integral over the region that it's enclosing of the partial of q with respect to x minus the partial of p with respect to y with respect to area. And what is the p function? Yeah, this whole thing, right? That's p. And this right here is your q, right? What's the partial of q with respect to x? 7. Right? 7 minus, what's the partial of p with respect to y? 3 dA, which is just 4 double integral over d of 1 dA. And this is the area of D. And D is not the unit circle with radius 3. The area of that's pi times the radius squared. So that's just 9 pi, isn't it? Times 4. So 36 pi. Wasn't that a little easier to do? A lot easier to do.
So
yes?
Green's theorem is always the route to go?
No, I'm going to show you an example now where we do it the other way. I'm going to give you a double integral that you don't want to touch, that you can turn into a line integral. And it's easy. So it's never one over the other. It's always the problem itself will tell you which way you want to go. But that adds some value to it, doesn't it? I mean, that's a line integral you could not do. Well, I don't know. I want to say you can't, but you'd be here for a while. So we can see sometimes computing a line integral over a closed curve is easier when we use Green's theorem to convert the problem to a double integral. There are other cases where we can convert the double integral into a line integral. So this is important, all right? I want you to all pay attention to what's going on here. So it's kind of tricky, all right? Do you remember that, I hope you remember because I've talked about it twice in the last 10, 15 minutes. The double integral over d of 1 dA is the area of d, right? That's what that is. And if we're looking at Green's theorem, right? Green's theorem, you have this partial q with respect to x minus partial p with respect to y dA. Then if this piece right here is 1, then that's the area, right? If that piece in there is a 1. So the question becomes, when would that become 1? Like what would q and p have to be to make this a 1? So this will be a 1 exactly when this piece here is a 1, yeah? So what makes it happen? Well, there's a couple of different scenarios. Let's look at this case. What if I tell you that the p function is 0 and the q function is x? Right? So what would the partial of q with respect to x be? 1 minus what's partial of p with respect to y? 0. And 1 minus 0 would be 1, right? So I could make this thing turn into a 1 if I say p is 0 and q is x. Here's another way I could do it. If I let p be negative y and q be 0, then I can also do it. So what's the partial of q with respect to x minus partial of p with respect to y? Partial of q with respect to x would be 0 minus partial of p with respect to y, negative 1, and then you get 1 again, right? So far I have two options that I could use to make that a 1 in there. And then there's also a way you could do it with some variation of the two. Right? What's the partial of q with respect to x here? 1/2 minus what's the partial of p with respect to y? Minus 1/2. So you have 1/2 minus 1/2 minus negative 1/2, which would be 1. Right? Understand? You sure? Okay, let me go back up to the first example because I think looking at Green's theorem, that's Green's, right? If I let p of x be 0, this is gone, right? Yes? If I let q of x be x, this is an x dy, right? Line integral over c like this. And this will be equal to, we know that will be a 1, right? So this will be, that's what this says right here. You see that? There's two other ways to do it, but I'm going to focus mostly on this one. Let's see why we would do this, all right? Why in the hell am I doing this? Find the area of the circle with radius r. Prove to me that the area of a circle is pi r squared, right? That's what I'm asking you to do? Okay. Well, do we agree with this? It'll be double integral over d of 1 dA. Do you agree with that? Where d is the region bounded by this circle. This is radius r, right? This in here is my region D. Now, we all know the answer is pi r squared. I'm asking you to show it's pi r squared, right? But do you agree with that? That double integral over 1 dA of d right there is the answer I'm looking for. But if I let, what was the one that we used right in the note before this? I said if I let p be 0 and I let q be x, then I can turn this into the line integral, right, over the closed path c of x dy. Is that right? So can you give me the parametric representation of this curve C? What's the parametric representation of it? R cosine t, r sine t. Do you agree? What's my restriction on t? 0 to pi, right? What I'm doing is I'm taking a double integral and I'm about to convert it to a line integral. This line integral becomes the integral from 0 to 2 pi of x. What's x? R cosine t. What's dy? Well, that's a derivative of this with respect to t, which is just r cosine t dt, right? Do y'all see that? That's x dy. Now, any of those things I can pull out of there? R squared, right? R squared can come out of that. What's left in here? Cosine squared. How are you going to handle cosine squared if you're going to integrate it? Power reduced. It's 1/2 plus 1/2 cosine 2t. But I'm going to pull the 1/2 out. So this will become 1/2 1 plus cosine 2t dt. And you should be able to integrate those. Do I have any questions on where I'm going here? This to that? Okay, which is 1/2 r squared antiderivative. So what is the antiderivative of that? T plus 1/2 sine 2t. Evaluate that where? 0 to pi. Okay, plug in 2 pi. 2 pi. What's sine of 2 times 2 pi is 4 pi. What's sine of 4 pi? 0. That's gone. So all I get is 1/2 r squared times 2 pi. Now minus, now plug in 0. 0, sine of 0, 0, 0, all gone? Okay. Which is pi r squared. That's it. Now look, again, we knew that the area of a circle with radius r is pi r squared. What I just demonstrated is how you can take the idea of a double integral, turn it into a line integral, and get the same result using Green's theorem. I need to zoom out of this one. This is a great example of proper usage of this. All right, if you were to go and plot this vector function, r of t equals, it's this in here, okay? 5 cosine t minus cosine 5t, and then 5 sine t minus sine 5t, like that. And you were to let t go from 0 to 2 pi. You would draw this epicycloid, which is this right here. That's what it would draw. What is the area of that? That's a very difficult problem to do, because you might be sitting here going, well, I know it's the double integral over d of 1 dA, right? Like, it's just that. It's the area of that region that it encloses. But you have to find a way of representing that region. And that region is not, it's not given to you in Cartesian, right? So it's not a Cartesian type 1 or type 2. And it's not polar either. I mean, well, it actually, no, it's parametric. It's truly not a polar region the way it's presented to us. So do you see that you're going to have a hard time coming up with limits of integration if you can't do this in Cartesian or in polar? However, this is equal to the line integral, right, over C of the closed curve in positive orientation of what? Partial, I'm sorry, no. P d x plus q d y. No. X dy. What I'm trying, let me put that back up there. Hold on. It's this, but for this to be true, P had to be 0, Q had to be X. So this turns into X dy. So do you think that there's a way that you can come up with a parametric representation for this curve? Well, they gave it to us, right? And are you going to be able to take the derivative of the x component? Absolutely. Do you know your restrictions on t? Yes. See? Everything is here for you to do the problem if you convert it from this to this. So let's do it. Should be the line integral. What are my restrictions on t? 0 to pi. Then it's my x, which is 5 cosine t minus cosine 5t times dy. So I have to take the derivative of my y, which is the derivative of this. So 5 cosine t minus 5 cosine 5t dt. And even though this may not look that great, it's sure is a lot better than where you were, which was stuck, right? Let's just distribute out and see if this is worth going after. 0 to 2 pi, let's see, 25 cosine squared t minus 25 cosine t cosine 5t. Middle one, minus 5 cosine t cosine 5t. And finally, plus 5 cosine squared 5t dt. Anything good happen here? Yeah, these two can go together. That's minus 30, right? Can you integrate cosine squared t? You can use the power reducing on that. You could do that on this one also. What about the middle one, though? Curious to know what you're going to do with that. (25 cosine squared t). What I think I'll do is I'll break these up into separate integrals. Plus, or I guess I'll do minus. Let me do this. 25 here minus 30. This is cosine what? Do y'all agree? Okay. Squared, yes, thank you. Okay? I think this one's doable. This one's doable. I'm more interested in the middle one. Let me see. This is going to be 25 halves integral 0 2 pi 1 plus cosine 2t dt. So I just used the formula on this, doubled the angle. Let me do the last one next. Plus 5 halves integral 0 to 2 pi. What goes in this integrand? 1 plus cosine 10t. Right? Just making sure you're doubling the angle, right? The 1/2 came out, and then this one. minus 30, integral 0 to 2 pi. How do you want to handle cosine t, cosine 5t? You're fumbling through those. Yes, that's right. You have a product to sum formula somewhere in your pre-cal formulas. No, we don't need to do it. Just there is a formula that allows you to split that out into a sum, and then you're in business. Yeah. I don't know about integration by parts. No, because it never gets better. So like if you use this for your u or something, you're always going to have like sine t, and then the other one you're always going to have the 5t inside. You're never going to get them both to have just t.
But can it be like one of those?
Oh, maybe like a reduction formula or something, or where it shows up on the other side. Maybe, I don't know. I'd have to work through it. I'd rather use that though, yeah. Okay, so let's see. Where are we at here? Let me just look at this one real quick. I know we're out of time. I'm just going to show you what this curve is real quick. 0, 0 to 2, 6. Back to 2, 0. Back to 0, 0. So you've got this curve that goes from 0, 0 up to here, down to here, and back over, like that. And you're trying to find basically the work done. Here's a vector field. And I'm going to offer this as a bonus due next class at the beginning of class, because I haven't really talked about how you would do this. I want to see if anyone can get it. All right? Yes?
Based off of what we've gone through today, do you think we could hit number 5 on the mini exam?
On the mini exam, yes. You could get number 5. Mm-hmm. Yeah, so you can pretty much do most of this. Yeah. Although I will say that number 5 is very much like this one, in the sense that, you know, the problems that I was doing before, I wasn't doing the vector field dotted dr like that. I wasn't using Green's theorem that way. But if you go through your notes and you look at things and the way we represent things, it'll all work out. So my answer is yes if you do a little more research, but no if you are just going to wait for me to show you, next class. That's why this is a bonus, though. Okay? Do it at the beginning of next class. Everyone have a great day. I've got to get to a meeting.